All right, so we're here for a Node.js performance optimization case study. There are a lot of slides for not a lot of time, but we're gonna power through this like champions. So, oh yeah, I'm Bryce Baril, by the way. I work at NodeSource. I'm the lead engineer on something called NSolid. I suggest checking it out upstairs. We'll do a demo for you. It's really cool, and it actually helps with a lot of these things. I'm not actually going to talk about it during this talk, though. All right, performance. So with Node and really anything, there's just two things that you're concerned with performance. One is how long it takes to do something. So we'll call that task completion. Often that's user experience, like how long my express route took from the user visiting it until they had the data and the response ended. And the second one is throughput. So how many connections per second can I handle? This is often to do with how many machines I need in production, that sort of thing. So we're going to sort of talk about both of these and why they're slightly different and cause you to use different tools. OK, so task completion. Work is done in a timely manner. This is user experience. This is most often in Node dominated by asynchronous I/O, file system calls, database calls, that sort of thing. And the key metric there is just how long it took. So task end minus task start. Pretty simple. Throughput has to do with blocking operations. So work isn't blocking other work. Usually blocking work in Node means CPU time spent on the CPU, or time doing garbage collection. And most frequently, you'll measure this in requests per second. However, it can also cause work time delays. So if you do have a long blocking operation, it can be measurable itself. Or if you have something like you have simultaneous blocking operations, they'll actually stack up. So if you have 3 requests come in at the same time, say like A, B, and C, and they're all going to take 10 milliseconds each, but they can't all work at the same time. So task A will complete in 10 milliseconds. Task B will actually take 20 milliseconds because it has to wait for task A to start. And task C will take 30 milliseconds because it has to wait for both of the other 2 to complete first. So you can get these cascading delays with blocking operations. So let's jump into our case study. So we're going to talk about glitching GIF images. This is part of an art project that I did a little over a year ago with some friends, where essentially we wrote some tools so we can read images, and then we can do all sorts of crazy things to them, and then write them as animated GIFs. So we're really going to talk about Glitcher in this case, which is the thing that does the image manipulation. So here's our workflow for doing performance optimization. If you're going to take like anything away from this talk, this is what I want you to take away. This is a pretty good workflow for every time you're ever going to need to try to optimize your code. And we're going to start off with step 0, which is it fast enough? Because honestly, if it's fast enough, you're done. Like, don't waste time trying to make it faster. You're great. But OK, so assuming it's not fast enough, you identify why it's not fast. So is it waiting for a database call? Is it blocking I/O? What's the nature of the problem? Because that's going to select the tools that you need to use. So based on what you've learned, you need to choose the tools that are correct for the job. Once you have your tools, you measure. You create a baseline. You try to find out location information. And you determine why things are slow. Once you know that, you identify where the problem's at. And then you can finally make the slower parts faster, because that's really what we're here to do, right? Once you do that, you have to measure again and really start all over again, because you have to check your baseline, see if you're now fast enough, and you can be done, or if you have to sort of go through this thing all over again and see if you can eke some more performance out. All right, so a word of warning, don't skip straight to step 5. This is sort of like premature optimization, but at least you know it's slow. But like jumping straight to like these V8 compiler tricks is not going to help you if you're waiting for a Postgres database query that's 5 seconds long, right? Saving 5 milliseconds when you're really waiting 5 seconds isn't going to really do anything for you. OK, so for our case study, is it fast enough? Obviously, it's not. For sake of time, I'm just going to say that I used logs to find this information. That's a typical place that you would find find out like you have a problem, or maybe you have monitoring, sort of metrics collection. And we're going to focus on something called replace background, which is just one of the manipulations in Glitcher. So identify the nature of the problem. So I know that the problem is blocking code because I wrote it, and I know that it's not making a database call, it's not making a network call, it's not reading the file system, it's simply inside of a function execution. So we're talking about blocked CPU time here. So now I know what tools I can use, but what if it was async, right? It could be an async problem. Well, you have a different set of tools, you have a different set of solutions. We're not going to talk about this, but here for posterity and anybody who's downloading the slide deck, which is linked right up there at the top. OK, so we wrote a test harness. In this case, for replace background, we're going to just take an image, look at all those frames, determine a background frame, and then replace what it thinks the background is with just a black mask. So what it looked like is sort of like a green screen effect. So here's our before image, little Drake doing some hotline bling. And here's what it looks like after. So you can see that it worked pretty well. Like maybe I could adjust the thresholding or tweak it a little bit. But given that it wasn't a green screen, it was actually able to do pretty well just by giving it any image and saying, get this effect for me. So let's look at tools. So we need 3 tools, or at least 3 categories of tools here. So how slow is it? Where's that slowness at? And why is it slow? So for how slow is it, we're going to use user bin time. Other tools I like to use are like Apache Benchmark or Siege if you're looking at requests per second, those sort of things. But these are our baseline measurements. For where the slowness is at, we're going to look at a couple of tools. So we're going to look at kernel tools, which will give you the full stack of information. And we're going to look at V8 instrumentation, which will actually just give you JavaScript information. And that is actually how NSolid works. OK, so let's measure. So we're going to use user bin time and do our bling2.gif, go ahead and run our test harness with it, and we see that it takes 8.67 seconds to do this, which is way too slow. This was a glitching tool that you could send images to, and it would send them through a pipeline and do subsequent multiple other glitches to them. And so the longer it took, the worse it was, and we actually would cut it off at a certain limit. And so an image like this would actually never even succeed. So there's all sorts of stuff here in user bin time that you can get, which is useful. So we can see the time it took, the total time elapsed, but this is really just the user time that we care about, that it was 100% blocked on CPU. We can get some memory information and then page fault information. None of this is really useful for us. In this case, we're focused on this 8.67 and 100% CPU. Oh, one other trick here. So time on your systems, it doesn't matter if you're Mac or Linux, is an alias. And so you can either call user bin time to get this output, or you can do a / time to eliminate the alias call, because the alias version is not as good. All right, so let's identify the location. So perf tool. So Linux perf tool is great. It's super powerful. You might have seen a demo on it yesterday if you were at the Netflix talk. I didn't go to that. I was busy, but I heard it was really good. So I use these instructions to get there. They're a little out of date, but you can just follow steps and it works. But it does involve installing like 11 system packages and a bunch of other things, and then collecting your data under the perf tool so that it outputs the data, and then massaging that data to generate a flame graph. So it's not trivial, but it's step by step, and if you follow these instructions, you'll be able to do it. And that'll generate a flame graph for you. We're going to reverse the order here. So here's a flame graph that we generated, and we're going to talk about how to read a flame graph. So the things that we're going to look at in a flame graph. So a flame graph, the x-axis is % of time during being sampled, and the y-axis is stack depth. So as we go up here, this function called this function, called this function, called this function, and so on, all the way up to the last little leaf nodes that didn't call any functions. And the width here is the % of time that was being sampled. And we're not seeing the whole thing because it's such a giant image. The things to look for, if we go back, plateaus. Oops. Well, now I just messed it up. OK, there we go. My speaker notes are all hosed now. Oh, well, I don't need it. OK. So here we can see some plateaus. We have this giant thing called average, which is just this big plateau and takes up a lot of time. We have these, which are sort of plateaus. And we sort of have this fat pyramid-looking thing here where each step is offset by the other steps. So these are the sort of things you're looking for, is anything that is towards the top that is really wide. Those are where you spend a lot of time. These things you don't really care about because they didn't actually spend much time on their own. They just simply deferred all of their work to other things. All right. So V8 Profiler. So V8 Profiler, the way you use this is it's all in the README, but you actually have to manually instrument your code. You take your code, you insert profile start, you insert profile stop. When the profile stops, you save that to a file. You take that file, you load it in Chrome DevTools. It's not a lot of work, but it does take manual instrumentation. It's sort of a lab operation, and you have to do it. But luckily, it only profiles JS, which for me, that's what I want. I don't do a whole lot of C++ work. In fact, I don't really do any. But so like Node Core people love using prof because they actually are working on Node Core, versus I tend to write JavaScript applications. So this usually works a little bit better for me. So let's look at the output for V8 Profiler. We can see that it agrees with prof that we really spent the majority of our time in average. And by the way, this view, you select this view by choosing this dropdown to select the heavy bottom-up view. Otherwise, it's a timeline graph, which is useful, but this is definitely the best view. So anyway, we spend 55% of the time exclusively in this average function. That's no good. So both of the tools agree. The location of the problem is in average. So what average is doing is it's taking all of the frames of this animated GIF and determining an average frame to make into the background frame. So what that looks like, oh, we're not there yet. OK. So let's find why it's slow. So we need another tool. So there's compiler tracing tools like Hydra or using flags. If you went to Mateo's talk yesterday, you saw him use trace-deopt. Does very similar things here. Just code review, looking at the code. There's probably static analysis tools out there. I've not found any that I really like for this, but I think that there's a big gap in the ecosystem there. So what if it was JavaScript or garbage collection? So since we know it's not, it would by the way, the garbage collection would show up in either of those two outputs. So we know it's not that. So there's different tools for garbage collection, mostly like ritual sacrifice. Good luck. I don't envy you. OK, so now we know where it's at. So let's make the slower parts faster. So these are generally the 4 reasons that I find that are the biggest reasons for poor performance in Node. Using the wrong tool for the job. Node isn't great at everything. Sorry, it's not great at crypto. If you're doing a lot of SSL, like use an SSL terminator, use Nginx, use HA proxy, use something like that, because Node simply isn't as good as that. Doing unnecessary things. If you think of your code as a set of instructions for the computer to work through, like the fewer things it has to do, the faster it will be. So look at your code. Like don't use things like promises and code paths. They're just adding a bunch of unnecessary work. Poor algorithm choice. It's very similar to doing unnecessary work. If there's a better algorithm for doing what you need to do, use that one instead. Like don't use bubble sort, use merge sort. That sort of idea. And then finally, not cooperating with the runtime or the compiler. And this is what people, when they're talking about like V8 optimization tricks, this is what they're talking about. how, using your named classes, because V8 does better with named classes versus something else. So how do optimizing compilers work? Well, there's a very simplified view. So JavaScript is really flexible. You can do whatever you want. You can change your number to an object and then to an array all in the same function, and it would all work fine. But the thing is we don't do that, right? That's silly things that while JavaScript lets you do it, you don't actually do it in practice. And because you don't do that in practice, the compilers are able to assume that you won't do it. So they take that information as you run your function. They say, OK, I've seen you do it this way all these different times. I'm going to assume that from now on, when I see this function, it's going to do this. So I'm going to eliminate all these edge cases, eliminate all these code paths that I don't see, and write some actually just pure assembly code that does what I think your function does. And then every time your function is run, it checks some safety valves to say, are you still doing that same thing? Yes, great. I'm going to use the super optimized assembly code version, which is great, and that's exactly what you want. But what happens when you de-optimize is that you've broken that assumption. You changed your inputs. You changed the way that you're using this function in a way that it hasn't seen before and doesn't work in the optimized assembly version. So it has to actually just completely pitch that optimized version of your code. And if you do this too many times, it will never try to optimize your code again. It'll just always put you in the tar pit, slowest possible representation of your code. That's bad. You don't want to be there. So how do we do this? Well, there's lots of talks out there, and I love to talk about these too, where there's all these tricks you can do with V8 to optimize how V8 uses your code. You can use named classes, you can avoid closures, you can do all these different things, inlining. But the thing is, V8 will tell you what it doesn't like. If you use these flags like I mentioned, or IR Hydra, it will say, I de-optimized your function here because you did this. So that's what you should do. You shouldn't just watch these talks and go and switch all of your classes to named classes because it's supposed to be better. Just let V8 tell you where to do it. So IR Hydra is the tool we're going to use for this. And by the way, I wanted to walk you through all of these tools, but with only 2 minutes left, there's no way that I was going to have time for any of that stuff. So if you can find me some point later, I would love to go through IR Hydra with you and show you all of these things, because it's super powerful and not easy to just jump into without a guide. But OK, so here's IR Hydra. And what it actually is showing us is a version of the assembly that it actually compiled down to. And here on the left, you have all of your functions that it's seen, and they're highlighted by de-optimization. So if they're just gray, they weren't de-optimized, which is great. If they're red, they had an eager de-optimization, which is one of the worst types of de-optimizations. There's also soft de-optimizations and other things. But then, so if I click on that function, it'll say I de-opted at this instruction. But the way I actually use this, we'll just go over here. So I've loaded up these two files in IR Hydra here. Oh, no. I have to load them again. OK. So we'll open this. OK. So now we can scroll down to average. So this is the view from the screenshot. But what we can actually do is click on source, and this will show you your actual source code. And code that actually has a representation is bold. Anything that never actually gets used is grayed out, because there isn't assembly code for this in our optimized function, because it actually never had to run any of this stuff, so it just skipped it all. Anything that's got this little blue down arrow has been inlined, and so I can actually click on this function and see the inlined function. And you notice there's no red mark here, so the optimization has to be in one of these inlined functions. So if I click on this, I can see the node buffer constructor, which has this little red flag which says, I de-optimized here. And if I click on this deoptimize, it says, you deoptimized because you read this arguments thing at object one, in instance 1, and it was actually only one length in array. So this is actually an out-of-bounds read deoptimization. But this is in Node core. This is not in my code, so this kind of stinks. So I can't really fix that as easily. So this is what it told us. Average function has an eager deoptimization, inline buffer constructor. So I actually did file a PR against this to fix this, and it was released today. So great. That didn't fix the problem. And really, there's no other output in this IR Hydra output that's really useful for this thing, because as it turns out, like these V8 compiler tricks are not always the right tool for the job. Sometimes you actually need to do code analysis and look at your code and figure out what you're doing wrong. So in this case, average calls median pixel. Median pixel obviously uses a median calculation, which requires a sort. So maybe there's an algorithm that doesn't require sort that I could use here to calculate the average frame. So turns out we're doing a lot of sort calls. We're doing 360,000 sort calls in this case for this image of 51 elements each, which is turns out kind of slow. So this is what the background frame looks like with median pixel. You can sort of see the background behind Drake and this weird, like, version of Drake. So what it does is then it takes every single frame and it determines the difference from this frame. And if it says that it's not really that different, it makes it the background image. Otherwise, it says, no, that's the foreground, and that's why Drake sort of floats in air while he's dancing. So what about mean, right? Mean doesn't take a sort. It just takes the data and determines an average. So here's what you get when you use a mean image instead. This TV just went out. So this might work, right? So it's still sort of a background frame. It's definitely different, so our output is going to be different. But let's see. Turns out it still works. In fact, it works well enough that it would be hard-pressed to tell me any difference between this image and the original one if I didn't show you them side by side. Side by side, you can definitely tell, but like it's pretty good. In fact, it's probably at least good enough, if not maybe even better. So let's measure again. Like, boom, shaved more than 5 seconds off, right? That's a significant improvement. It's down to 3.4 seconds. Awesome. So now we can do a flame graph again, and we can see that, remember this is proportional? So this looks like it's bigger, but really it's just proportionally more time. And these are proportionally less time, which is great. It's not perfect. Like this now maybe is something we should look at. This is INX search. Here we have this new thing called buffer copy, which wasn't in the original one. This is this giant plateau. And if we look at V8 profiler output again, like now we're spending 40% of our time in copy, but average is way down here at 6% now. So we've significantly improved things there. So we're pretty happy, but we can still go back to step 0 and figure out, what went wrong. Is there anything else we can fix? Can we reduce the instruction count? Can we choose an even better algorithm than mean? Can we look and optimize something else? Like, sure, there's lots of things we could do. We don't have time to go through all these things. I did do one thing. I did remove the call to buffer copy just by manually doing the copy and shaved a full other second off. So I'm confident that we can get this down under a second. Like, that would be awesome. But we're going to stop there, and hopefully that's some insight that you can use to do some of these performance optimizations on your own. So finally, check out NSolid. It makes it a lot easier to do some of these things, like capture a flame graph, which is a push a button without like installing all these packages or choosing some platform-specific tool. And my goal with NSolid is to make everything in this talk possible at the push a button with NSolid. So give it a try. There's demos upstairs. That's it.